conducting this public viva was examination, and with the along with the research supervisor, I invite Shri P. Valsaraj to defend his thesis on the title Engineering Friendly Alternative Methods for Wind Speed Assessment and Forecasting for Wind Energy Applications. Mr. Valsaraj, the platform is yours, and you can proceed with your presentation, and you are invited to defend your thesis. All the best to you. And on behalf of the board, I once again welcome all the spectators who have joined in hybrid mode, both in online as well as in physical mode. All the best to you, Mr. Valsaraj. You can go ahead. Thank you, Professor.
Thank you, madam. Good afternoon and welcome to the presentation of my thesis titled Engineering Friendly Alternative Methods for Wind Speed Assessment and Forecasting for Wind Energy Applications. Wind energy, as we all know, is one of the few energy options for addressing the issue of energy crisis and also the related ill effects of climate change, global warming, etc. So, wind energy development and utilization have been happening across the world at increased rates. And for deciding and designing a wind farm, and also for managing the electricity generated from wind, we need to have wind resource assessment as well as wind forecasting. And these tasks are done normally by measuring the wind speed at a higher altitude equal to the hub height levels of wind turbines. And it's an engineering structure, this wind mast. And installation and maintenance of wind mast for longer periods is a difficult task from the practical perspective. And in my work, I am trying to employ shorter and engineering-friendly wind masts in combination with some data-driven methods so that wind speed at higher altitudes can be predicted. And before going into my work, I will just try to give an overview regarding the status of wind energy. And as at the end of 2019, the global electricity generation from various sources is given here. The coal is the major contributor, and wind-derived electricity comes to around 5.3% only. So other sources are given. Now the growth trajectory of installed wind electricity generation is by 2019, onshore based it is around 594 gigawatts and offshore around 28.31 gigawatts. So it's a high rate growth happening in the field of wind energy development. Now, if you look at the ranking, country-wise ranking, as at the end of 2019, India came fourth with 37 gigawatts. China was the first. Now, how the wind electric generator, or usually called wind turbine, works. This gives you a picture regarding the engineering aspects. See, this gives the front view and this gives the engineering side view. See, the wind, while blowing through the wind blades, will the kinetic energy will be transferred to the wind blades. It will rotate the hub. The hub will rotate. I will show within the nozzle there is a generator and the electricity is generated like that. One aspect I want to emphasize here is this is called hub height. This is the tower, and we have to measure and forecast wind speeds at that hub heights in the industrial applications. So see, this is the nozzle I have shown, This is the hub. Here is the blade. Here, blades come here. So the rotation is transferred through gear system to the generator. The electricity is conditioned to the required level and taken out through cables. This is how wind electric generators work. Now, how important wind speed is in determining the wind power. Wind power output is given by this equation, where you can see V is the velocity of wind speed. So it's a cube of velocity. So minute changes in wind velocity will affect the power greatly. For example, if velocity is doubled, the power will be 8 times more. So velocity of wind is very important. Now I told you about the hub height. Over the years, wind generators are coming with increased hub heights and enhanced capacities. For example, in 2020, commercially available wind mast, the highest one was 153 meters in hub height. So 153 meters high. We have to measure the wind speeds at that level. So in the coming years, it will again increase. Now coming to wind, what is wind? Wind is, as we all know, the movement of air mass from one region to other caused by pressure difference, and the pressure difference is caused by uneven heating by the heating and cooling by the sun. It's a clean fuel, free of cost, it's available, it's renewable, it never gets depleted, it gets renewed, and it's a form of solar energy. It's a solar derived thing. In fact, it's a kind of solar energy. Now the global wind system, I will just give a brief thing. There are three main groups. It's prevailing winds, periodic winds, and local winds. Under prevailing winds, three divisions are there. You might have heard these words: trade winds, polar easterlies, prevailing westerlies, like that. Now this represents our Earth, and I will just briefly say the global air circulation system. Main one is this. All happens because some regions get heated up quickly and some regions slowly. Towards the equator, near the tropical regions, more sunlight is sun rays reach, and so there it will get more heated up like that. Because of that, and along with that movement, due to the rotation of our Earth, the centrifugal and Coriolis components of forces acting on the moving wind mass. Anyway, all these together have produced some wind circulation cells. Here it is shown in the northern hemisphere. It's called polar cell, Ferrel cell, Hartley cell. So here, this one near the surface, the wind flow will be like this. So like this. Here it will be the reverse, and here it will be like this. Similarly, in the southern hemisphere. So approximately we can put them within these ranges of latitude. This is called polar easterlies, prevailing westerlies, trade winds. Now, periodic winds is normally the monsoon winds. This happens, the land gets heated up quickly and gets cooled also compared to the sea surface. And because of that, the air mass on a seasonal basis moves from sea to the land. That's a monsoon. That's called periodic winds. Local winds happens every day during daytime from sea to land, sea breeze. Nighttime from land to sea, then valley breeze and a mountain breeze. From the top of the mountain and deep inside the valley, cooling and heating will be at different rates. And just to give you a picture, this is one land-based wind farm. Just to give you an idea how a wind farm will look like. And this is an offshore one, sea-based, water body-based wind farm. Now, as I said, wind farm design and wind farm management. Wind farm design, whether to decide whether to install a wind farm, we have to first study the wind resource available there. That's called a wind resource assessment. At least 1 year. More than 1 year is well and good. So at least 1 year you will have to, for covering the entire cycle, seasonal cycle, you have to measure the available wind. Then only you can decide whether to go ahead with the wind farm. And also how to decide and design the layout. And once the wind farm is set up, wind is an intermittent resource. So to grid integrate this intermittent resource, you'll have to forecast its availability and accordingly adjust the other resources. There comes the importance of wind forecasting. So I'm concentrating on these two aspects in my research. Now I'm coming to wind mass. Wind resource assessment as well as wind forecasting requires collection of wind data at the required height. In the wind energy industry, it is normally done using wind mass. Different kinds of structures are possible. I have shown one lattice mast and a tubular mast. And on top of it will be connected anemometers and other many sensors also will be connected. And we will take the data. That is how wind resource assessment is done. Now other attachments to the wind mass are anemometers, of course for wind speed, then wind weight, vane for wind direction, then pressure, temperature sensors, humidity sensors, then data logger. All these things are connected to this wind mass structure. Just to give you an idea, this is a lattice type wind mass. So you have to put so many guy wires to support it and all. I'm coming to the engineering complexity of such structures. Now this is a tubular type wind mass. In the inside picture you can see how that wind anemometer is connected. So in fact this is one of the wind mass involved in the wind assessment study done by UNERT and the data from which I have utilized in my study. Now wind assessment, wind resource assessment involves these different aspects. Data collection from the wind mass. Then the data collected from a wind mass can be extrapolated around it. That's called micro survey. So once you take the wind data at a point, you can extrapolate it, of course, by inputting other parameters, climatic and terrain parameters. You can extend it to a wider area. That is called micro survey. Then comes micro sighting. Once the micro survey is over, exactly at what all points you have to position the wind mass, that is decided in micro sighting. We have different software packages for micro survey as well as micro sighting. Micro sighting depends on the characteristics of the wind turbine as well. Now coming to wind forecasting, the time ahead forecasting, as I told you, is essential for effective wind energy grid integration and its management, like real-time grid control, efficient load dispatch planning, whether when to operate the resource, because this is an intermittent one. Then marketing. So, of course, for maintenance, when wind is not available for a prolonged period, you can schedule the maintenance. So, for different aspects, you need to have wind forecast. Then different forecast horizons are there. Generally, there are different classifications. This is the one I prefer to present. Very short, medium, long, very long. We are more interested in short-term forecasting, which is for the energy grid integration of wind-based electricity. Now there are different methods for wind forecasting: physical methods, statistical methods, artificial intelligence, and hybrid methods. And here comes the machine learning techniques also. I have used this machine learning techniques in my study. Now my research covers three different areas. One is vertical extrapolation of wind speed using data from shorter wind mass. So a height above interpolation from the given type. Wind forecasting. And then I have obtained some computationally effective approach for wind forecasting using machine learning based methods in the case of wind time series. Then I have tried to put forth some simplified masked structures wherein you can use shorter wind mass in place of the taller and difficult structures. And using this shorter wind mass, you will try to get time ahead forecastings at the required higher height. Now, this is the symbolic regression based improved method for vertical wind speed extrapolation. This is for at the present time, at a given time, we have a wind at a smaller height. We want to see the wind speed at the higher height at the same time. Now, in industry, generally for this purpose, we are using an empirical equation that's called power law. Suppose V2, V1 are two velocities at h2 and h1. That is the equation. And where alpha is called the wind shear coefficient. So like that, V3, again, two other difference. So you can either use one velocity and height, and by knowing the alpha coefficient for that particular area, you can calculate the other one. Otherwise, take two known values, two known sets, find the alpha, and for the third one, you apply that alpha. But this empirical model is only approximate one. It's erroneous also sometimes because of the issue. Simplifying assumptions in model building, shear coefficient calculation, error associated with that, and different levels, different shear coefficients. In my study, I have plotted the wind shear coefficient for the same location. It varies on a time of the day basis and also on a day of the year basis. So wind shear coefficient is not exactly constant. That also causes errors. Now symbolic regression, how it works. Now we use symbolic regression normally in complex nonlinear systems for modeling such systems. In traditional regression, what we do is we'll first predefine an equation of fixed form to model the data, and the regression process will try to find out the parameters and coefficients, optimal values. But in complex nonlinear systems, predefining the model structure will be difficult because of lack of knowledge of the entire theoretical aspects. So in such cases, symbolic regression is a better suited candidate. In symbolic regression, carefully selected blocks, building blocks like of mathematical operators, functions, variables, and coefficients, they will be selected together, and they will be combined randomly and recombined several times repeatedly using the evolution biological evolution principle. It's actually based on the genetic programming principle. And each time a fitness function built in the algorithm will detect the best fitting solution and retain it for further reproduction and mutation process. And the less fitting ones will be abandoned then and there. And this process continues until the model structure as well as the parameters and coefficients are obtained, the best suiting one. That's the principle. Yes. In my study, so I have selected 4 locations, windy areas. So L1, L2, L3, you can see here that L1, L2 is 25 kilometers apart. L3 is 34 kilometers from L1, then 136 kilometers, and highest and longest 326 kilometers. I will use 10 minutes data at 20 meter, 50 meter, and 80 meter for a year period. This gives the wind flow pattern on a monthly mean basis. So in June, July, August, high windy season, like that. This for the 5 locations. Now, I used the symbolic regression tool available named Eureka as our basic tool, and using that tool and using the data of say one particular day, I have shown this day only 1 June 2013 at location L1. This is the way the ranked solutions I am getting from the symbolic regression process. So the best one, I took this one. It produces an error of root mean square error of 0.24, the lowest one. Like that, it increases. So this is taken as the solution, symbolic generated by symbolic regression. And like that, I used the try to do it at other locations also. See, for L2, the most fitting solution is this one. For L3, when you use the data from L3 and make a function, symbolic function, you are getting like this. For the 5 locations, this is the symbolic functions. Now, how that coming to the L1 point location, how that symbolic function, this is the symbolic function we use. Using that, I compared that alongside the power law, how it functions in relation to power law. Here you can see how the actual one, the one predicted using symbolic function, the one predicted through our power law are pictured here. This is the one in terms of this error metric, symbolic function is better here. This is another day of the year. Here again, symbolic function based solution is better. And I showed only for 1st June and some, I think 1st February. Other typical days of every month I have shown. Throughout, you can see the power law. The symbolic regression based one gives less error. So the supremacy of symbolic function based solution is shown here over the power law method. Now, based on wind speed based, as the wind speed increases, how that error is coming using these two. This is the symbolic function based one. You can see as the wind speed increases, error is coming down. Of course, it is the same for power law based also, but overall, this is better. The improvement is better in case of symbolic function. So this shows at higher wind speeds, it's better to use my symbolic function based solution. The schematic of how it works is like this. See, at one location you have to install a power one. In my case, this is 20, 50, and 80. H3 is 80. So using this, you make a symbolic function using this h1 velocity and h2 velocity. How to get? After that, you can forget this one. So this symbolic function is taken at other different locations. You need to install only a shorter one, h1, h2. And here you can use the other the function derived from there and use here. This is the way it works. So this is symbolic function at L1 versus power law for location L2. I used the same function generated at location L1, and that I took that to location L2 and applied both there. So again, in that case, this is 25 kilometers away. In all cases, all monthly cases, SEC symbolic function based solution is giving better results with the lower RMSEs. Again, another location L3, 34 kilometers away. Here also I am getting superiority for the symbolic function based method. But while going away at 136 kilometers, sometimes power law is improving. Again, at 326 kilometers away location, again, sometimes here and all symbolic function is better, but sometimes its efficiency is diminishing. And this shows the entire picture. That's the symbolic function generated at location L1. I applied it at L1, the same one at L2, same at L3, like that. Now, in overall, if you take all these, 52 out of 65 cases, around 80% superiority is given to is shown by symbolic function method. Whereas if you take the symbolic function from L1 and apply it at L1, the symbolic function from L2 and apply it at L2, like that, then all are better than our industrial method of power law method. Now, I took 1 day data size for deriving the symbolic function. I also tried half day, 3-day data, 5-day data, and 7-day data. This is the one we use for L1 case. Now, this is how the data size affects on the performance. So here, too less a data size is not advisable. 1 day is okay, is the better one. And if the data size increases, there is no improvement, whereas it decreases, increases the error. So there's an optimal data size. In my case, 1 day is optimal. Now the advantages of this method, it's a better method than power law. So within, I think, some 35 around 50 kilometers around, you can definitely use this one. Far apart, we can use maybe some other reference wind mass for deriving another symbolic function. Then complex tall mass structures can be avoided. That is a very advantage for the wind industry. And as I told you, as I shown you, more effective when wind speeds are high. It's a required the condition for wind farms at higher wind speed. There it is well suited. The limitations, as shown, the distance from the reference location to the test location increases. Its accuracy is coming down. In one reference location is must first for getting the data and forming deriving equation. After that only you can go in for shorter ones. One at least one is required as a reference one. So I have suggested some further studies also, different combinations. Including incorporating other geographical and environmental aspects into the modeling like that. These are possible for our studies, other further studies. And I have published a research paper based on these findings. Applied energy, it's an international journal from Elsevier with an impact factor 11.4. Now in part 2, I was trying to find out some computationally friendly method for wind forecasting using machine learning method. So machine learning, you all know, the computational program learns itself and improves from the previous data. The algorithm used in the program detects the pattern of data, and that information is used to predict the future case. Different algorithms, these are all common algorithms. My intention was not to improve the algorithms and the model. So I used the commonly available SVM regression, random forest regression, k-nearest neighbor regression, gradient boosting machine, distant tree regression, and exploratory regression like this. I used E1071 package in for the development, training, and testing of models. Now, in this case, the research approach, the same locations. I took data in 2013 for training and tested it on the data of 2014. The wind speed data for the first year, 2013, used for training and validating the SVM and RF models. First I did using these two models, then for corroborating only I did the other things. The wind speed data for the second year, on that testing was done. Now we employed the mutual information technique to see to optimally select the number of data points to be considered for the training and testing. See, mutual information gives between two random variables gives the level of dependency between those two variables. In this case, how one wind speed is affected by its previous wind speeds. So the mutual information curve, it comes down as the delay increases. Speed took after this period it's constant. So up to this we took it like that. Up to that 72 data points are influencing the one ahead. So for training and testing like that, we have done. And these are different time ahead predictions using model trained at L1 is tested at L1 itself, like that, L2 at L2 itself like that. And delay and mean root means per errors are shown here. You can see from this graph, see, if you take 20 hours ahead, for example this one, that is L1 at location L1, up to 20 hour ahead predictions will come down with RMS below 1.5. Like that, this graph is used for that. In the next thing, the cross location scenario was tested. That model tested at trained for location L1 was taken to L2, L3, and L4 and L5 for prediction. This is how that averaged root means for errors for different time ahead predictions are plotted. Now I tried for the other 4 combinations also. This is another way of representing. See, if you take 3-hour ahead prediction, for example, this one, different cross location scenarios, it all gives errors below 1.5 meter per second root mean square error. Because at the period, the hour increases, its accuracy is coming down with more error. This is another way of representing. See, all the different time ahead predictions were taken, and for example, this one gives, this is percentage of predictions. If you take 1.5 meter per second, 15 hour ahead predictions using RMSE, approximately 32% of predictions are coming with RMSE below 1.5. If you are satisfied with the 2.5 meter per second RMSE value, of course, some 75% of predictions. In that way, this picture gives. This is of course with the support vector machine SVM regression based analysis. I did the random forest based also, and it is superimposed on this. More or less similar pattern at higher time ahead predictions. Some one model is slightly better than another. That's all. In a sense, it's almost similar results. And I applied other algorithm-based models also, and this is a RMSE for different algorithm-based, and this is another metric, statistical error metric, mean absolute error I applied. Now the relevance of this research outcome is actually for forecasting, every time you have to train the model adjacent to the testing and then do the testing prediction process. So it's a time consuming, computationally intensive. Here you can train the model at one location, and that one you can take to other locations for prediction. So computational efficiency and productivity increases. You can in fact use a hardware component and put that train part in it and use it somewhere at other locations. Yeah, this is another publication based on this study. I have published another paper in International Journal of Sustainability. It's a journal from the House of Taylor and Francis. Of course, this is the one I told you. Then there is another international conference paper also at the Central University of Kerala. In the third part of my study, I was trying to replace the taller mass with a shorter mass. Here I have taken 2 cases only, 2 locations only, S1 and S2. This is the wind flow pattern. Yes, these are the 5 methods. Method 1 is the conventional method. So I have data at 20 meter, 50 meter and 80 meter. The method 1 is the conventional method. You take wind data at the 80 meter height, forecast wind data at the 80 meter level. The second method, the simplified one, is you take wind data at 50 meter and predict at 80 meter. The third one, here I'll come to that. Here you have to install a reference mass for some time for training period. After that, you need to retain 50 meter mass. Here again, the third one is you need not install a reference mass 2. Just install a 50 meter mass and take data at 50 and 20 meters, and from that you can predict at 50 and 20, and using power law extrapolate it to 80. That's the method. And method 4 is further simplified. You install a 50-meter mast for say 1 year, take data 20-meter and 50-meter, train the model. After that, you dismantle the 50-meter and retain only the 20-meter mast. Then you can predict the 80-meter after that. And then method 5 is the cross-location scenario is incorporated. You install one mast for reference at one location, take the data and train the model, take that to different locations where you install only 50-meter mast, and there you can predict up at the, this is a time ahead prediction at the 80-meter level. This is the block diagram showing that for the method 2, as I told you. The principle is, say, wind speed at, say, for example, I am at 80-meter is a function of the same at 50-meter, whereas the 50-meter is a function of 72 points backward. So instead of training a one step ahead, sorry, forecasting one step ahead at 80-meter, we are training as well as testing with the back data corresponding to the lower level. Like that, this is the method 4. Now in method 1, I am trying to show, I split the time series into 6-hour segments, different segments, and for different 6-hour segments calculate the RMSE. This is the spread. These 6-hour segments here. This is how the RMS values comes. The best fitting line is like this. It's almost parallel, showing that the accuracy level of the model goes on unchanged, almost unchanged. This is another way of representing the percentage of how many of these predictions are coming below different limiting RMSE values. Say 1.5. If you take 1.5 meter per second as the RMSE, roughly some 85% of these component RMSE components coming below that level, like that. So this is for method 1. This is a conventional method, and this is for method 2. The similar approach, method 3, method 4, and method 5. I put together that part in here. Of course, this is the conventional method. It's the best one. Others are less in accuracy. This is another representation. Throughout the 1 year span, I calculate RMSE. Here again, the same thing is shown. Method 1 is the best one with the lowest level of error. So, but there are some advantages from the practical perspective. Here, as I told you, you have to retain the 80-meter mast. You know, it's a complex one. When the sensors, such things go down, you will have to de-erect, correct it, re-erect. So many spaces required, so many difficulties. But here, some the error is there, some slight error is there, but some friendliness, engineering friendliness is there. You need to install 80-meter for some time only. After that, you need to install retain 50-meter only, like that. So this is the advantage. Only by compromising slightly your accuracy levels, on the other part you are getting greater advantages. I tried the other way also. Earlier one I tried at the S1 point. This is the attempts at the S2 level, the other point. So here again, almost similar trend is shown. Then again, I applied the some other gradient boosting machine regression and KNN also. I initially did on SVM only. So this is the comparison. So slightly from this method 1 for S1 location, S2 location, like that. Slightly these are better in some cases, and in general, the approach is working. And the relevance of this one told you. The forecast accuracies are coming down. Engineering friendliness, the ease with which the mask can be installed and maintained is good. Of course, this can be used in a way for wind speed as estimation also. You can adapt it to like that. Just one hour prediction like that, you can take assessment also. In method 5 is the cross location facility incorporated. That is a more interesting to the industry, so more studies are required there. Of course, more optimization for that cross location thing. Different combinations of altitudes we can make a study. Better performing algorithms based models and hybrid models might give better results. And again, these findings I have published as a research article in the International Renewable Energy and Environmental Sustainability. It is a journal from EDP Sciences, France. So here I have the publication I have just shown. I have an IEEE expert paper in the international conference. And method 5, we have applied for a patent, the granting of which is awaited. Then the key outcomes of my PhD research are these. A new and improved data-driven method has been developed for wind speed extrapolation to higher altitude using wind data measured with shorter wind mass. The second one I would like to say is the computationally friendly method has been proven in case of wind speed time series. And lastly, the new 4 alternative methods, by compromising the prediction accuracy a bit, you can have greater advantages in the engineering aspect of the wind mass. These are my publications, 3 papers in international journals, and 3 conferences, and a patent awaiting. That's it from me. Thank you all.
Hello, Mr. Valsaraj. It was very lucid and very appreciable presentation. I congratulate you on behalf of the board. The work that you have done also is real time, so that always assumes a lot of importance. Instead of choosing a hypothetical problem, when you work with a real time problem, it is really appreciable and a welcome one.